Let's talk about processes. In previous videos, we've encountered several systems: a puddle, a tree, a town, an open pit mine, and a stream. We also drew simple diagrams of those systems. If you haven't watched that video or you need a refresher, you can look in the description down below. Today, I want to talk to you about some processes that occur within those systems. First, I want you to think about a machine that cooks food or makes you a nice warm beverage. This could be a microwave, a stovetop, an oven, etc. You place your food or beverage in or on the machine, and a transformation occurs. What is that transformation? What happens to the food or beverage? How simply can you describe this process of transformation while cooking? Speaking of which, I have a mug of cold water here. Some people think it's weird, but I actually like drinking hot water. Not tea, just hot water. I'm going to go heat this up in the microwave. Let's consider the microwave. We'll draw a system as a box, right? What are the inputs to the system? Let's draw energy as our input. What's the output? What process happened? Well, water was heated and there was some waste heat generated. You may have noticed that I didn't draw cold water as an input or hot water as an output, and I'll explain that soon. So this is an example of a process. A process is something that happens within your system. So here we have the process of heating water. Processes might be chemical, biological, or physical. In the case of heating, like water in a microwave, the process is physical. When you turn on the microwave, electrical energy is converted to microwaves. They vibrate the water molecules in your glass and they heat them. In the end, you have hot water. When you think about engineering processes, it helps to think about batch versus continuous processes. Batch processes are those that occur without any material inputs or outputs over the time of interest. These occur in closed systems. Continuous processes have material inputs and outputs over the time of interest. These are processes that occur in open systems. The idea of a time of interest is important. For batch processes, for example, you may load the system before the process starts. When you cook or when you heat water in a microwave, for example, you place a cup of water in the microwave. You might initially think of this as an input, right? Because you're putting the cup of water in the microwave. However, for the process of heating water, while you're heating the water, the door of the microwave is closed, and no matter is entering or exiting the microwave as the water is heating. Therefore, our simplified system of the microwave is a closed system, and the heating process is a batch process. When you're thinking about processes, you should also consider if that system is at steady state or if it's transient. This consideration has significant mathematical implications that I'm going to talk about in a different video. Sometimes you may want to assume that your system is at steady state even if you know the system is in fact transient. You're going to have to use your engineering judgment to determine if that's a reasonable assumption. A steady state system is one where none of the values you're measuring in your system changes with time. If we go back to the microwave example, it's definitely a transient system. Over our time of interest, our time of interest is while the microwave is heating the water. During that time, the temperature of water is going to be increasing, so the system is transient or non-steady state. Let's look at each one of the systems we encountered during our walk and the processes that occur within them. First, we looked at a puddle. Maybe we're interested in processes like algae growth, metals dissolution into the water from the soil, or solar heating of the water over the course of a day. Are these processes batch or continuous? If we assume that no matter is flowing across the system boundary, then they're batch processes. This is probably a reasonable assumption for algal growth. It may be a reasonable assumption for the metals dissolution if we've included the rock surface in our within our system boundary. Are the processes steady state or transient? In all of these processes, the puddle properties are going to change with time. The concentration of algae or metals might increase. The temperature of the water changes during the day. Therefore, the processes are all transient. For a tree example, processes could include how the tree uptakes or releases nutrients or water to the environment. If we're interested in phytoremediation and we want to know how the tree uptakes metals and where the metals go within the tree, all of these are continuous processes. Matter is flowing across the system boundary. It's not immediately clear if these are transient or steady state processes. It may be that you could make a steady state assumption here. This would depend on the time scale you're considering. That is, the tree mostly uptakes metals, nutrients, water at about the same rate, especially if you've limited it to a single season. As you think about this example, especially if you consider like rain events, seasons, drought, etc., you may start to realize some of the nuances of making this assumption of steady state. For the Berkeley pit, maybe we're interested in a water balance process or a dissolution of minerals into the pit lake, or how pH or safety of the water changes over time. The process of the water balance is a continuous one. Water flowing into and out of the pit lake across the system boundary. This process may also be assumed to be steady state because in general these flows aren't going to change very much with time. However, if you're looking at the process of the pit water level changing over time, then it's going to be transient. So whenever you have this idea of changing over time, or if a question that you encounter ever asks you something about how things change over time, you're going to know that the system is transient because you have to look at that change over time. Regardless, system modeling is much easier if you can assume that the system is at steady state. So you may find that you want to make this assumption whenever it's reasonable. Again, that's going to depend on your system, the processes you're considering, the relevant time scales, and what exactly the problem is asking you. Finally, for this stream, let's say we're interested in nutrient cycling or changes in nutrient concentrations over the length of stream that we're considering. So maybe we're looking, we could look at that, or algal growth, fish populations, water levels, etc. So all of these processes are continuous, right? Because you have water and nutrients, metals, fish, whatever, flowing across your system boundaries. Depending on the question you're answering, you might be able to make a steady state assumption, provided those concentrations of algae, fish, your water level isn't changing much with time. However, if you're looking at how those things change with time, you're going to be looking at a transient process. So again, it depends on what question you're trying to answer. The same exact system, the same exact process might have different assumptions that you're making depending on what question you're trying to answer. Now you've seen many examples of processes that occur within systems. And it's very likely that you may be able to think of more than I've mentioned here. Processes and reactions can occur in systems that are at steady state, where there are no changes in your process variables in your systems with time. Let's take the example of nitrogen in a stream, right? So nitrogen in streams is an issue because they can cause eutrophication. This is where excess nutrients or nitrogen leads to algae overgrowth, and then the algae die and decompose. Their decomposition uses oxygen in the stream, and the low level of oxygen can kill the fish. If we look at our stream and our diagram here, you can think about this process from two perspectives. If you see yourself as a small volume of water traveling down the stream, you could experience changes in nitrogen concentration, depending on a number of factors, like nitrogen decomposition. I've drawn a graph of nitrogen concentrations over the stretch of the stream. However, if you look at the stream as a whole and measure the concentration of nitrogen at several points along the stream's reach over time, you may find that the concentration in each point doesn't change with time. That is, the graph that I drew here isn't shifting with time. That makes the system steady state. This is kind of a confusing point, so take a few moments to think about it. And convince yourself that you can see changes in a volume of water traveling through your system. However, if you're measuring at different points in your system, you might not see changes with time, making that system steady state. That concludes our intro to processes. Remember that a process is something that happens in a system. While several processes are occurring in the system that you will be studying, focus on the process or processes relevant to the question that you're trying to answer.